Hello, Professor. First, I apologize for the quality of the video. This is really the best I can do with what I have. But I figured it would still be nicer to have a video of the animation. That way, you don't have to go through and figure out how to run everything and mess with it yourself. I mean, you're more than welcome to, but I figured this would be nicer on you. So first, let me run. I have three animations, one for frequency design and two for state space, as these are the only ones that are stable. So first, you can kind of see how this is pretty stable, and there's not a whole lot of movement. Like you can see, the cart's position moves 0.035, and the amplitude of the pendulum swings is 15 times 10 to the minus 3 radians. So it's really not going to be very noticeable. But even so, I'll run the animation. So I don't know if you were able to catch that, how quickly that came. Let me try to rerun that for you. Yeah. So it's very faint, very faint. But I mean that's essentially what we were expecting to see, since this was very faint as well. So next we have state space. Close all, clear all, Control C. I apologize. My mat. Oh my. Thank you. Okay. CLC, clear all, close all. Why is it struggle to close things? Very frustrating. Um. Okay. So this section now we talk about control design. Let me run this. So we don't care for this one, we care for this one. You can see precompensator with LQR control. This is going to be a lot more visible, uh, because as you can see, it moves to zero point 0.2 meters rather than minus 0.035 as before, and our radians does change by about zero point 0.7 minus 17 point minus 0.17 up to about 0.06. So you should see a little bit more. For state space observer, state space LQR. There we go. And let me run this. So you can see a lot more right there. I don't know why it was glitchy, but let's run that one more time. Uh, there you go. That was a lot smoother. And you can see how it was very nice, very nicely controlled. So next, let's look at observation. Let's see. Will it give me my plots? Oh, this is happening again. That's unfortunate. I dislike when this happens. Okay. So this is with observer-based feedback control. So it's very similar as to before. Now when I run it, it takes in the new data and it plots it again. Let me run that one more time for you, if it will let me. There we go. Thank you. Yeah. Okay. Now we could have also animated the other ones, but they were pretty unstable. Like if if I was to go through my report over here, frequency response, this is root locus response. Why is this PID control? No, this is root locus design methods. So if we did this, you can see how while the impulse is stable the pendulum angle is stable, the cart is unstable. So if on this, essentially what would happen is this ball right here would move a little bit, but this cart would fly off the screen after about 7 seconds or so. So there's really no point in animating it. And in the next section of the video, you're going to see the animations on the Simulink side. For this section, just very quickly, I wanted to talk about the function I used. So essentially what this does is a lot of this section right here is to create this system or this function, and this takes in it's a for loop, and it takes in each part by each part. So for here yk1, let me just show you what this looks like. Um, so yk, instead of k, I'm gonna put a semicolon. So this is the position of the cart. So it takes each one of these positions and it plots it frame by frame with the time vector and with the the angle vector too of the pendulum, and it just plots those side by side. So that's how the function works. Okay, this should end this part of the video. Next part should talk about Simulink. Hello, Professor. So this is the Simulink section. So this one is the Simscape model with the same PID control that we used in the MATLAB section. So let's run it. So you can see here, very stable, 2.5 seconds. If we looked at the scope, we can see that the angle is fine, but if we ran the system forever, it looks like the position is not fine. The position goes up to infinity. So if we run for 10 seconds or something, oops, let's stop the model. Excuse me. If we run it for longer, it'll eventually go off screen, I believe. Yeah, so you can see that the model is going off screen. Yeah, so that's essentially what this one is. Minimize this. So had we not included the PID controller and simply just left it as is, so here's the system with no controller and it's just the single impulse, and when I run it, I'll leave it at 10 seconds, but when you run it here, it just flies off screen, which makes sense if you take a look at the scope here. You can see how it's moving between plus and minus pi. This here switches after pi, it has to go back to minus pi. And that's just the pendulum saying that it's spinning forever like a windmill. And in this case, the position is somewhat exponentially increasing in terms of position, so it's just getting faster and faster. So it's as unstable as it can get. So that finishes the Simscape section. Let's take a look at the Simscape multi-body section. So this one is similar, it's just using different models. So let's run it. Should take me to MATLAB. There we go. So this one again has the PID control. As you can see, the pendulum is very stable. The issue here instead is the position is once again unstable. As we take a look at the graphs right here, you can see here how the velocity starts and is constant, and the position has a constant change. So it's unstable, as PID controller has proven. And if we use this manual switch to take off the PID controller to take a look at just the disturbance force, we're going to see a lot more instability. If we run it here, it's going to spin like a windmill, just like we saw in the previous one. This is flying off the screen. If we take a look at it slowly, it's just going to keep doing that. Continue fitting it to view. Just going to continue to spin and fly off screen. Well, that should end the animation section of this. I hope this helped, and it saved you some time with having to run our own code. feel free to reach out if you have any questions regarding anything that you saw.